So power series make our lives easy because we can estimate values of complicated functions using polynomials or using the series itself. And integration and differentiation of polynomials and these infinite series is much easier than integration of these more complicated functions. So if you're going to use approximations by Taylor polynomials, there are two things you should probably master. One is actually being able to calculate the Taylor polynomial as the function, and the second thing you should master is Taylor's theorem for the error to give you some control over the error you might be making, or at least some awareness of what error you might be making with your approximation. So let's work our way through an example. Let's find the third Taylor polynomial of f of x equals e to the x, and this time we're going to estimate values of e to the x around a equals 2. So the appropriate series to use is the Taylor series at a equals 2, and we're going to truncate this after the degree 3 term. So on the left I have a graph of the function y equals e to the x shown in red, and I also have a graph of this third degree Taylor polynomial, which is f evaluated at 2 plus the first derivative at 2 times x minus 2 plus the second derivative at 2 over 2 factorial times x minus 2 squared plus the third derivative at 2 over 3 factorial times x minus 2 cubed. So this is a cubic, and you can see that the graph of this Taylor polynomial in blue here does indeed look like a cubic. And now the value of the function at 2, f of 2, which is e squared, is actually equal to the value of the Taylor polynomial at 2. For values of x close to 2, this is a reasonably good approximation for values of e to the x. However, at x equals 0, this is no longer a good approximation to e to the 0, which is 1. In fact, at 0, the value of t3 of 0 here is negative. So this third degree Taylor polynomial is going to be a good approximation to our function in intervals centered at 2, as opposed to intervals centered at 0, which we were looking at before. Now, of course, when I differentiate f of x equals e to the x at 2, I'm going to always get e squared. So this polynomial, this third degree Taylor polynomial, is e squared plus e squared times x minus 2 plus e squared times x minus 2 squared over 2 factorial plus e cubed times x minus 2 cubed over 3 factorial. This is a reasonable approximation to values of e to the x for x near 2. Our next question is, could we have some estimate or an upper bound for the error we might make if we use this approximation for values of x between 1 and 3? And notice 2 is right in the middle of that interval. Well, here's where Taylor's theorem comes in. We have whatever the remainder is, r3 of x here, its absolute value, which is e to the x minus t3 of x, which is the absolute value of e to the x minus t3 of x, has to be less than or equal to m times the absolute value of x minus 2 to the 4 over 4 factorial, where m is the maximum or an upper bound for the absolute value of the fourth derivative of f on this interval. And of course, we know that the fourth derivative of f is e to the x, and it maxes at x equals 3 on this interval. So the value of the fourth derivative of f at 3 is e cubed, and Taylor tells us that the absolute value of the remainder, or the error we might make, for any x in this interval is less than or equal to e cubed times the absolute value of x minus 2 to the 4 over 4 factorial. Now, of course, for any x in this interval, the absolute value of x minus 2 must be less than or equal to 1. So the absolute value of the remainder must be less than or equal to e cubed over 4 factorial, which is 0.837. So for any x in the interval from 1 to 3, the maximum error we might make when we approximate e to the x by this third degree Taylor polynomial is 0.837.